We'll get started in a couple of minutes. I think people are still joining. In the meantime, please confirm if you're able to see my screen and hear me clearly. Great, thank you. Okay, let's get started. Welcome to the week 4 live session of the GPU Architectures and Programming course. Hope the course is going along fine for all of you. And I think there have been a good amount of hands-on assignments and MCQ based assignments, right? So hopefully you're getting to understand some of the concepts better. So I think all of you are familiar with the live sessions, so I'll just skip this. And if anyone's joining for the first time, all you need to know is that this is a 2-hour session, and please keep it as interactive as possible. Ask your questions, doubts, try to give answers to the questions that we discuss. That's about it. And around the 1 hour mark, which is 8 o'clock, we'll take a 5-minute break so that you don't get overwhelmed by 2 hours of continuous information thrown at you. So today we'll mostly be covering the topics that were taught in week 4, which is very simply multidimensional data and synchronization. So in the multidimensional data, we looked at multidimensional grids, multidimensional blocks. We spoke about how do we map kernels to such data. If you had 2D data, if you had 3D data, what would be a good way? Then we also looked at the concept of synchronization. What is synchronization? When do you need it? And how do you actually do it in code, right? So these were the topics that were covered in week 4, and we'll be focusing on these today. So before that, I think there were 2 or 3 interesting questions that I got last time, so I've picked those up. So the first question was, integrated GPU uses up the CPU RAM itself. Is there some kind of reservation that's done for this? So I think last week I told you that mostly there is no reservation, right? But today I'll give you a slightly more detailed answer than that. So what happens? So these screenshots are from my own laptop where I have 32 GB of RAM, right? So if you see here, I don't know if this is very visible for people without a monitor. Let me make it slightly bigger. So here I don't have a GPU, so it's an integrated GPU. I don't have a discrete GPU, let me put it that way. So you can see two fields here: total available graphics memory and dedicated video memory. So a small portion of the RAM is set aside as dedicated video memory. So you'll also find the same field in a discrete GPU, but there this dedicated video memory is actually part of the GPU's memory. It's not borrowing it from the CPU DRAM. But in this case, this 128 MB is actually fixed. It's completely set aside for the integrated GPU. In that sense, there is a reservation. But everything else is dynamically allocated as and when the GPU requests for something. But there is a maximum limit on that. And again, these details can change from operating system to operating system. It can change depending on the hardware vendor, right? So I'm just giving you one example here. So 50% of my RAM is set aside for the GPU. So here again, when I say set aside, it doesn't mean that the maximum memory that my CPU can use is 16 GB. It doesn't mean that. It means the opposite. The maximum memory the GPU can use out of the CPU DRAM is 16 GB. But the 16 GB is not reserved, in the sense that if the GPU is using just 2 GB, then the CPU has the rest of the 30 GB free for its own use, which you can see here, right? So the GPU memory being used is around 2.1 out of 15.9 GB. So only 2 GB out of this maximum 16 GB is used, which means that the rest is free for the CPU to use. Whatever is unused can be used by the CPU. So the reason to not have a hard and fast reservation is very simple. If I said that 50% of the memory is just for my GPU, then there might be applications where the CPU needs more than 50% memory and the GPU is not really using up that its quota of 50%, right? So we don't want to run out of memory in those cases. So that's the reason not to have a hard and fast reservation. Instead, we say as and when the GPU needs it, the memory will be dynamically allocated. But a small amount of video memory is reserved, and these are for certain legacy applications, for certain very special corner cases, which we won't go into here. But broadly, understand that there can be a maximum limit on how much of the RAM the GPU, integrated GPU, can use. That's all you need to know. So hope this answers the question on how integrated GPU uses up the CPU RAM. Are there still any doubts on this? And you can check this in your own laptops, right? Laptops or desktops, or even if you have a GPU machine, you can go look at this and see what you get. This is from Windows again. There might be different ways and different terminologies that are used in Linux. So you might have to look up the commands and see how you get this information, but you will be able to get the equivalent of this information on any operating system. Okay, if there are no doubts on this, let me move ahead. Right, the next question was, suppose we had two operations, one add and one subtract, in the same kernel function. Will one thread work on both operations, assuming that the thread ID computed is same for both the operations? So by default, the way we've been learning to write CUDA programs, right? In that way, if you just had one kernel where you had these add and subtract operations, one following the other, and the thread ID computed is the same, as in both act on the same element, then it will be one thread working on both the operations. I don't know if the person who asked the question is here, but maybe the intention behind the question was this add and the subtract are kind of unrelated. So if the same thread is going to same thread is going to compute both of them, then I'm kind of unnecessarily increasing my execution time, right? Maybe that was the motivation behind asking that question. So that's why I put in this extra line around CUDA streams, right? So if you have the way to have concurrent execution here, for instance, if you wanted the add operation and the subtract operation to happen at the same time, then what you would do is actually define one kernel with an add operation and one kernel with a subtract operation, and you can use an advanced feature of CUDA called CUDA streams, which will help you execute both of these kernels concurrently, meaning at the same time. But again, this comes with a caveat that you might not want to do this all the time, right? Many times in a kernel, it is not just one statement. If you take a convolution kernel, for instance, you will find many statements. And the reason, of course, that they are there in that function or in that kernel is that all of those statements together form the convolution operation, and usually there is some dependency between them also, right? But if you wanted to do something like this, where you think you want to execute multiple kernels concurrently, then you simply write them as multiple kernels and make sure that they go to different streams. So if I have one kernel defined for stream 1 and another kernel defined for stream 2, then it is possible that both of them execute concurrently. That is the answer to this. Any doubts on this? If not, let's move on. The last question, which I think I already spoke about last time, but I've just put it into slides also so that it's very clear for whoever asked the question. So the question was, how do GPU threads compare to CPU threads, right? So first, I think we spoke about the programming perspective in detail last time, and that is a difference. So for CPU threads, maybe you have something like a pthreads library, and you explicitly call threads using pthread create. You define what the thread does, and then you define the way it kind of merges, joins, all of that stuff, right? Whereas in GPU, if you talk about the programming perspective, you're writing code as if it's going to be for one thread. For instance, if I write an addition operation, I just write AI equal to BI plus CI, right? I don't have to write explicitly. At a programming level, I don't need to define the behavior for each thread. That is done automatically. So that's from the programming perspective. The other thing is, when I talk about threads in the CPU world, it could be that the CPU threads do completely different things. For instance, I might have one CPU thread that is continuously doing logging of some kind, while the other CPU thread does some computation, right? So this thread is measuring maybe how much time it takes for the computation, how many resources the computation takes, while the other thread is just constantly doing the computation. So the CPU threads have no relation in what they are doing in this example. But in GPU threads that kind of execute in a single warp execute the same task, except when there is some divergence due to branching. But most often, GPU threads are executing, because it's again a case of SIMD, or more specifically with GPU, SIMT, right? So you have all of these threads executing the same thing. So that's again a difference. And then the final difference comes from the way GPU threads and the way GPU architecture is, that GPU threads are much more lightweight as compared to CPU threads. So these are some of the differences that I could think about. There might be more that you guys have in mind. Feel free to talk about it, or even think about it offline and think how these two are different, because I'm sure all of you have studied CPU threads in maybe your C programming or your OS course, and now you're, for the first time, maybe you're studying GPU threads. So it might be good to compare the two. Any doubts or questions on this? Okay, if not, let's move to the next thing. So I think that was it for the doubts from the previous week. So now we'll go through a few topics from your week 4 course content. And again, if something was not clear in the course material or something that you didn't understand from the videos, please ask about it. I'll either explain it right away today, or I'll come back next week with maybe a simpler explanation than what is there in your course slides. So feel free to ask, saying this topic or this definition is not clear to me. That's the point of having these live sessions, right? Okay, so moving to, we start off with a multi-dimensional block. So in general, when we talk about a grid, you can think of it as a 3D array of blocks, and every block in that array of blocks is a 3D array of threads, and you can specify this using the dim3. And whenever you see x comma 1 comma 1, it means that those dimensions are unused, the ones that are set to 1. That's kind of the convention we use. If you see no ones, then it means that it's a full 3-dimensional specification. If you see 2 ones, then it's a 1-dimensional, and if you see 1, then it's a 2-dimensional. That's how you interpret it, right? But you have the functionality for both of them to be a 3D array. Moving forward, so the grid dimension variables, again you have x, y and z. It can start from 1 and go all the way up to 2 power 16. Now again, remember that many of these things change with architectures, right? For instance, how many threads you can have. I think 1024 is what you learn, right, in the course. But whenever you're trying to do this for maybe a later generation GPU, always go look up, and just even for curiosity's sake, right, you'll be able to see what is the difference between maybe Fermi that you're learning in class, Fermi or Kepler, right, mostly what we're learning in class is. You'll be able to see the difference between that and the latest GPU. But yeah, for now that's fine. And every block will have a block ID, and again that block ID is given by all three x, y and z, right? And any thread in a particular block will see the same block ID variables, because again it's in the same block, right? So every block is determined by this tuple of 3 values. So any thread in a given block will again have the same value of block id.x, block id.y, block id.z. And the block id xyz should belong to 0 comma grid dimension dot xyz minus 1. You can again figure that out using this, right? So that's about it. So let's look at maybe an example. If this was not clear through the class, this should kind of help you understand better. So we call the vector add kernel with x comma y, and x is defined using the dim3 as 221 and y as 422, right? So this is your array of blocks and array of threads. Now let's look at the grid and the block structure. So the convention here is Z, Y, and X, right? For all of them, for both the block IDs and for the thread IDs. You'll notice that in both places. So now the X dimension goes from just 0 and 0 to 1. The Y dimension also goes from 0 to 1, and the Z dimension, recall that 1 means unused, so the Z dimension is just remains constant at 0. So that's about the grid, about the block IDs in the grid. Then if you go to a given block, let's say we zoom in on this block, you'll have a number of threads, right? And each of those threads again has its coordinates as z, y, x, right? So those three coordinates are given by this dim3. So your here your x value goes from 0 to 3 because it's set to 4. Y value goes from 0 to 1, and z value also goes from 0 to 1. So that's what you see here. So this should be clear, I hope. Yeah, this is another example where you're also given the how do you calculate the block number, how do you calculate the thread number, how do you calculate the global thread ID. And yeah, we'll look at this through some questions in today's problem solving. So let's move on for now. So synchronization, right? So let's talk about, before we talk about an example for synchronization, one thing to remember with GPUs is that the scheduler doesn't guarantee you any particular order of execution of the blocks. It just, every block can execute independently, meaning I can execute block 1, block 2, block 3, or I can execute block 2, block 1, block 3, or any other order that I want, right, as a GPU scheduler. So why is this important? As a programmer, when you write GPU code, you should be aware of assumptions like this, right? If you write your program assuming that blocks will execute in a certain order, then that's wrong, because as a programmer you are not given that guarantee by the scheduler. The scheduler says that I'm going to execute it in any order I want, right? So that's important to know. And this is what, so basically because you have this flexibility, or because you don't have any constraints on order between blocks, it enables more scalability, because I can execute as many as possible, right, without worrying about any synchronization or any sort of ordering between them. So that's one of the main reasons why we get good scalability on the GPUs. So when we talk about synchronization, we are talking about constraints that can be enforced to threads inside a thread block. And how is this done? Using the CUDA construct called sync threads. And this second part will come later on in the course as to how threads share data and cooperate with each other. For now, we will talk about synchronization from the perspective of how do you enforce certain constraints on threads inside a thread block. So yeah, I think this was an example that was discussed in class 2. So here you have each thread performing a sum, right, of certain number of elements, and then finally I think the last thread goes and computes the total sum. So this sync threads almost looks like a barrier, right? And you might have heard the word barrier in some other maybe communication courses, or maybe you haven't heard of it, but this synchronization is kind of a barrier in the sense that all threads are forced to wait at this barrier. They cannot cross this barrier until everyone finishes. So that's the way you think of the synchronization. And the code is very simple, right? You just need to put one line saying sync threads, and that will automatically cause this to be enforced. So that's, I think, a very simple example. So apart from what I've covered, or in what I covered just now, are there any things that are unclear that you guys would like to see in more detail? Anything like that? Any questions, doubts? I'll give you 30 seconds to think about it. Okay, synchronization. I see. Okay, so let me see if I can get something to draw with. So let's say I have threads that are in a block, and that are, this is my time axis, right? So now without a synchronization, let's say each of them, like in this example, you have different amounts of work that is done by each thread. For instance, here one thread is adding up all of the elements, one thread is adding one less than whatever is in this column, and so on, right? So one assumption that you could make is that the threads all do not finish at the same time, and this may or may not be true, but given that the work is not equal, we could expect that the threads finish at different times. For instance, in this example that I have here, this thread takes the longest amount of time. This one takes slightly lesser, this one even lesser, and this one finishes first. Now, if I had to do some computation that was dependent on the result of all of these computations, I cannot start it here, right? Nor here, nor here. I have to wait till every single thread is complete. So think of this as kind of a barrier, right? So if you have maybe sort of a game, I don't know if you have a game like that, but let's say you have some race or something like that where your course is divided like this. It's a series of races, right? So maybe you have 3 races like this. So everybody starts from here, and then the first race is over. So different runners run at different speeds, and therefore they might reach the end point at different times. But now to start this next race, I require that everyone be present. So that means that I have to wait here, right? That's the equivalent. That's a layman example for what synchronization is, and that's why we use this sync threads call, which will enforce that your program waits till all of these threads finish their computation and arrive at this point. So think of it as kind of a barrier that waits till all of the threads have finished whatever is here. In this case, it is just computing the sum and updating it here in the V element, right? So that's where you call sync threads, and that means that, so what the other question is, what happens if I don't call sync threads, right? So this last one that computes the total sum might give you some wrong result. Why would that happen? Again, at the time that this starts execution, one or more of the other threads might not have finished their execution, and therefore when you try to do a sum, you use certain wrong values, and as a result of that your overall computation is wrong. And this matters. This is kind of a very small example, but you could have hundreds of threads that you've defined working that way, right? So it's very important to realize where these points, where do you need this synchronization. That is the first thing that you have to kind of think about as a CUDA programmer. Do you need a synchronization? The other thing to remember is that you're at this point you're forcing all of these threads to wait, right? So unless it is really needed, it would kind of be like a waste of time, right? So where to put these synchronization calls is also a kind of a key question to ask yourself. But why synchronization is needed, I hope that is kind of clear. Did this help? Okay, great. Let's see what I had next. So that was the end of the recap topics. Again, any other topics people didn't understand or you'd like me to explain, or something that looked too complicated to you, we can always come up with simpler examples, right, to explain any concept. So if not in today's live session, I'll definitely be able to do that in the next live session. So feel free to ask. If something felt too complicated to you to understand from the lecture material itself, we can try to find a different way that makes the concept clear. Anything? Okay, let's move on. So I picked up, I think there were two questions from the last week's live session to this week's live session. So I've just picked them both up from the discussion forum along with the official solution. For any of you who haven't seen the discussion forum, this might be a good reminder to kind of go check it out. But yeah, so this was, I think, based on the class material. So one particular slide spoke about grid dimension being 6 comma 2 and block dimension being 5 comma 4, right? So given this, your number of blocks should be 6 into 2, which is 12, and the number of threads per block should be 5 into 4, which is 20. And but in the discussion that was presented as part of your course material, the number of blocks is mentioned as 20, which is wrong. It should be 12. So that's the correction that is also issued in the discussion forum. So it should be 12. So whenever you go through class material, always try to work it out on your own and confirm if what is presented is right. Sometimes it might happen that the instructor had multiple examples and forgot to change one thing while changing the example, right? So always try to work it out independently and see if your understanding matches what is given in the lecture notes. And if it doesn't, feel free to ask a question. So this was one thing. The other thing was that there is no mention of any particular dimension, 3D, 2D or 1D, in the grid and block dimensions while launching the kernel. So this was regarding the hands-on programming assessment. So the question was, does it matter if we choose 1D or do we have to choose any of the others? So you're free to choose anything based on your understanding. So typically if something is not mentioned in the question, you're free to choose something based on your understanding. But if it's unclear or you feel confused by that, again ask a question specifically like this person has asked, and you will get a reply from the TAs who evaluate your programming assignments. So I think those were the only questions on the discussion forum. Okay, so let's move on to the problem solving session. Before that, any other questions or doubts that you've had so far, not just in week 4, but maybe week 1 to week 4? Are there concepts that are still unclear, things that you are still finding difficult to understand? It is an advanced course, that's why I'm asking. That too, some of you might not have had a computer architecture course or might not have used a GPU or CUDA before. So it's okay if something is difficult, but feel free to ask about it. Okay then. Let's move on to the questions. So, compute kernel 1, this is the sample function that's given to you. Only the inputs and outputs are specified to you. So, this takes two 1D arrays named input 1 and input 2 of total size, data size, processes them and writes to an array named output after performing the following operation. So the operation is output of I equal to input 1 of I star input 2 of I star 4, and the launch configuration is given as three-dimensional grid of 4 2 2 with two-dimensional blocks of 32 32 1. What is the value of data size given the following launch kernels? So I'll give you 2 3 minutes for this. Try and solve it, and then we'll discuss the answer. And feel free to put your answers on chat. It doesn't matter if it's wrong. Is the question clear or is it too confusing? Okay, we have one answer, option D. To the rest of you, is the question clear? Are you working it out or are you confused by the question? Okay, please explain. Sure. So, this is a function that is given to you. So, we looked at some sample examples, right? For instance, not this, right, this one, where you're trying to launch a kernel. In this case, it's vector add kernel with the following three dimensions for your grid and your block. We also spoke about what those three dimensions mean. So here similarly for this sample compute 1 dot kernel, you are given the launch dimensions. You are given that the launch dimensions are 4 2 2 for the grid, and for the blocks it is 32 32 1, right? And you are given what the kernel does also. So what you are asked is, what is the value of data size? So how would you figure this out? Think about it. So from the launch configurations, what would you get? And remember that the data size is the total size of the input 1 and input 2 arrays. And you can make that assumption that every thread operates on one point. So what do you need to figure out this total size? That's the question. I've already given you one hint. Every thread operates on a single data point. Can you figure out the number of threads? If you do, what can you do with the number of threads and the totals and the number of what can you do with the number of threads and the assumption that every thread operates on a distinct data point? Okay, we have one more answer. Is the question clear now to everyone? Okay, 4 and 4096. Okay. Right. We have someone who's written down the total thread. So let's discuss the solution now for anyone who hasn't gotten it. So the answer is 16,384. How do we get there, right? So first of all, how do we get the total number of threads? And as someone has pointed out on chat, you get that by multiplying the number of blocks into number of threads per block. And given that you have a three-dimensional grid, you multiply 4 into 2 into 2 to get the number of blocks, and to get the number of threads per block you multiply 32 into 32 into 1. So number of threads would be the multiplication of both of these together, 4 into 2 into 2 into 32 into 32 into 1, which gives you 16,384. Now remember the assumption that I said, that every thread operates on a distinct data point. So you have this many threads and you know that each one of them operates on one element. So then what is the size? The size is going to be the same as the number of threads. So that's the answer. I'll pause here for a minute because I think some of you are confused by the question. Think about the solution and let me know if you have any doubts after this explanation. Is something still unclear? Anyone? Or is it clear now? Okay, I will. Okay. Confused how to fix launch parameters given a problem statement. Okay, that will need a concrete example as you say. So what I'll do is to note this down and then come back to you with uh, an explanation for before the next session. So I think talking about it with an example will make more sense. So yeah, let's do that in the next session. That's a good question. Thank you. Any other questions or doubts? Okay, let's move on in the interest of time. So, I have a similar question, I think. So, we have a compute kernel 2 now. This takes as an argument a 1D array named input of total size data size, processes and writes to an array named output. The input array to this function will be the output array obtained as a result of uh, process under, okay, you can take this to be compute underscore kernel 1, basically from the previous question. And the following operation needs to be performed here: output of I equal to input of I multiplied by input of I, and the launch parameters are given to you like this: 2 comma a comma 1, 8 comma 8 comma b. So you are expected to find a and b here. Again, I'll give you 2 3 minutes. I think it might take you a while to read and understand the question also. Any answers to this, or is how to proceed from whatever is given in the question clear, or is it confusing? Okay, 8 comma 16, we have one answer. Right, the data size is 16384 as in the previous example. Anyone else? Are you stuck somewhere? Are you trying out a particular approach and somehow that isn't working? Okay, let's take a look at the answer and see. So it is 8 comma 16. So let's see how we come up with this, right? So one simple way is to use a constraint of maximum number of threads per thread block. That is known to be 1024, right? That's a fixed thing. So given 8 comma 8 comma b, how do you get, how first of all, how do you get the number of threads per thread block? You multiply all three of these, right? 8 into 8 into b, that should give you 1024. So which is the value of b that gives you 1024? It is 16. And in this set of options, you're lucky because there's just one option with 16. So you don't even have to calculate a, right? So you straight away go and say this is the answer. But here's the other thing I want you to keep in mind, right? So you might think at this point that the rest of the question is irrelevant. So does the kernel even matter? Given any kernel, I could ask you this question. I have 8 comma 8 comma b. What would be b? And it would be 16, right? Because your maximum is 1024. So what does the rest of the question have to do with this setting of a and b? So that's where if you had two options with B, then the other thing you would need to do is to verify whether the product of these two comes out to be 16384. So as we saw in the previous example, we are always assuming that one thread operates on one distinct data point, right? Unless we specifically mention in a question that it's different, that assumption is going to hold. So now, given that assumption, you know that the size is equivalent to the number of threads. So you know the size already as 16384 from the previous question. So what you need to ask yourself is, how many threads do I need to do that 16384? And you've already found out B to be 16. So now take the product of all of these things and check what value of A gives you 16384. And the value of A that would do that would be 8. And that's how you get this answer. Is that clear now? A is equal to 16 and B is equal to 8. Okay. So the product would remain the same, and your number of threads per thread block would also be within 1024. So I don't see why it's not valid. It would be a valid launch configuration. And if both of these were your options, then both of them are correct, because I can't see any reason why the other one would be wrong. So yeah, there can be multiple valid launch configurations. Sure. Any other questions on this? Is something still unclear, or is it mostly clear? Yeah, so we just used this to get the answer. The block dimension is limited by the total number of threads possible. So you have a few examples here where you multiply all three and see if it's within 1024, right? So that's what we did in this question. But additionally, if there are different options which add B equal to 16, you should also do what I spoke to you about, where you multiply both of them and check if the total number of threads corresponds to the data size. Is this clear? Any doubts? Okay, it's clear. I'll just wait a few more seconds. Okay, let's move on. Right. Compute kernel 3 takes as argument an 1D array named of input of total size data size, processes and writes to an array named output. The input array to this function will be the output array obtained as a result of process kernel 2. Again, take this to be compute kernel 2. It's probably a typing error in the question. The following operation needs to be performed here. Output of I equal to input of I star I, using a one-dimensional grid of dimensions a, 1, 1 with two-dimensional blocks 128, b, 1. What are the possible values of a and b? Again, a very similar question as the previous one. So maybe now this will be easier for everyone. Okay, we have one answer saying 16 comma 8. Anyone else? Use the same kind of logic that we used to solve the previous question. What is the maximum number of threads? What would you set B to so that it falls within that maximum number? Anyone? Is this still confusing? Okay, let's look at the answer and then see if you have questions. Maybe that will help. So, again, let me repeat. So, you're given the block dimensions, right? So, if, remember from the previous question where the block dimension is limited by the total number of threads possible in a block. That is 1024. So, if I give you a few block configurations like this, maybe we'll go through this in a little detail since I didn't get many answers for this question. So 512 into 1 into 1 is 512, which is less than 1024. 8 into 16 into 4 is also less than 1024. It will come to 512. 32 into 16 into 2, which is 32 into 2 is 32 into 32 is 1024. That is also fine. 32 into 32 into 32 is not fine because it exceeds 1024, right? So whenever you are given a block dimension x comma y comma z, first thing you need to do is to check if the x comma y comma z satisfies this 1024. So going back to the third question that we were trying to solve, you are given 128 comma b comma 1. So what would you do? You would your b has to be such that this 128 into b into 1 is less than equal to 1024. So you try out all these options. If you try out 128 into 8 into 1, you get 1024. So obviously if you try out 16 and 32, it will be greater than 1024. So that's not valid, right? And again here it's like a short circuit. The moment you see b equal to 8, you know there is only one option with b equal to 8. So you pick that. And this might be useful when you're solving MCQs for timed exams, right? For instance, GATE. So always think about starting off with an approach that is not very lengthy and that can help you eliminate a few options. And if you get lucky, that speed will help you pick an option very quickly, like you do here. But what I was telling you in the previous question, if you had two options with b equal to 8, then what you need to do is to see if the total number of threads is equal to the number of elements. So again here it is 16,384, I think. So both of these are 1 comma 1, so that's fine. So you basically have 1024 into a equal to 16,384, right? And this is your simple linear equation, so you need to solve for a. And if you do that, you will get a equal to 16. That's about it. So now hopefully how you get A and B is clear. Although for the both this question and the previous question, you didn't need to solve for A. Solving for B is enough because there's only one option with that B. Is this clear? someone who still has doubts in this sort of question. By the way, these questions are all picked up from previous year NPTEL assignments, right? So it's good for you to understand it well, because you might get similar questions in your future assignments or in your exams, right? They're not questions that are artificially created, they are picked up from previous iterations of the same course. Is this clear? Okay, I think we are at the 8 o'clock mark. So let's take a 5-minute break, and I'll see you guys at 8:08. My clock shows 8:03. So I'll keep the call running, but we'll take a 5-minute break. Okay, let's continue from where we left off. So the next question, consider a kernel launched with the following launch configuration: 2, 2, 1, 32, 32, 4. What is the total number of CUDA threads that are spawned for the given launch configuration? This is a very straightforward thing, I think, compared to the questions we've solved so far. So, okay, wrong question. What exactly do you mean by the wrong question? I see. Okay. That's a fair point. But let's assume for now, like I said, this 1024 limitation also is architecture specific. So let's assume that this number of threads per block is valid on a particular architecture. Then what would your answer be? 16384. Okay. Anyone else? Anyone else? Okay, let's look at the answer. This was a fairly simple one. So, yeah, it is 16384. But yeah, the initial point that this is the number of threads per block exceeds 1024 is a good one, right? Given that in class we've discussed architectures which only allow 1024, ideally such a question should be invalid. That's a fair point. But hope this store how you calculate total number of threads from a launch configuration is clear to everyone. You multiply all 6 elements, right? That's what you need to remember. But why we do that is basically number of blocks into number of threads per block. So the block and per block cancel out and you're left with total number of threads. Any doubts in this? Okay, we'll keep moving. For the launch parameter configuration provided in question 4, what are the minimum and maximum values of thread ID x.x? So I'll just scroll back to the launch configuration. You can note it down if you want. 221 32 32 4. This is the launch configuration. What is the minimum and maximum value of thread ID x.x? Okay, maximum min is 0, maximum is 31. Okay, anyone else? We'll just wait a few seconds and look at the answer. Okay, let's take a look at the answer. So, how do you get this from the launch configuration? The answer is right. It's minimum of 0, max is 31. So, going back to your block dimension, you see that block dimension dot x is 32, right? From here, right? And from that, uh, you get that the threads in the x dimension would have thread IDs ranging from 0 to 31. So the minimum is 0 and the maximum is 31. Any doubts here? I think this is straightforward again. Let's move on. I think most of the questions in week 4 are fairly similar, right? Because syllabus wise, you don't deal with a lot of assignment 5 model questions. I haven't. That will come in the next week. Like I said in the beginning, right? In every week, we kind of target 1 week syllabus because it's 12 weeks and 12 live sessions, so it's easier to do it that way. But I think from the perspective of your assignments, the assignment deadline might be before we discuss, right? So that's something you have to deal with because this time I think the live session started 1 week after the course. So, week 5 assignment questions, we will explain very similar questions next week, but I don't know your assignment deadline and I'm guessing it's somewhere in this week. So, that might not help you from the perspective of the assignment, but we'll definitely discuss those questions. Any other questions? And if anyone doesn't remember, I'll just go back to this example we had in the recap slides. Right. So this is how the block and the grid and the block look like, right? So here are your launch parameters, and here are your block ID Z, Y, and X, and Z, Y, and X. And like we said that times, if you have 4 as your what is specified in the dimension, the value actually ranges from 0 to 3, which you can see here. So this is X, and X would be the last element here. So if you see these values, it ranges from 0 to 3. So similarly, in the example that we are working out now, we are given 32. Sorry, wrong question. We are given 32. Yeah, that same kernel launch configuration is used. So the 32 would be, is that the one we just discussed? Yeah, that's the one we just discussed. So min is 0 and max is 31. So let's move to the next question. Again, a very similar question. For parameter configuration 2, 2, 1, 32, 32, 4, what are the minimum and maximum values of block ID x dot y? Any answers? Take your time. I will give you 2 minutes to solve it. Okay, in a 3D launch, how do we get the global thread ID? Okay, in the meantime, keep solving this question. Let me see if one of the recap slides I had talks about that. Okay, 0 comma 1, anyone else? 0 to 1, okay. Okay, let's look at the answer for this. It is 0 to 1. So grid dimension dot y is 2, as you can see from here. So again, thread blocks in the y dimension would have IDs with values 0 and 1. So let's do one thing. I'm still trying to find the slide for the 3D launch. I'll do that in the background while you guys solve questions. So we'll go back to that at the end of our problem solving session. So I think we have 2 or 3 more questions left. So after that, we'll go back and discuss the how do we get the global thread ID. And if you're still confused, I'll talk about it again in the next session. So let's move to the next question. Consider a 1D CUDA kernel that operates on a 1D array A of size 204A with launch parameters 32, 64. Each CUDA thread operates only on one data point. On what data point will the thread with thread id dot x equal to 20, block id dot x equal to 20 operate on? Assume that thread IDs along the x dimension represent rows, thread IDs along the y dimension. This might be relevant for this question, so that's fine. So choose the correct option. Which element does the thread with the following IDs operate on? I'll give you 2-3 minutes. In the meantime, I'll look up the global thread ID. Okay, 1300. Anyone else? Oops, sorry about that. Okay, I think everybody has gotten the answer, so let's anyway look at that. So how do you get that? So you do block idx dot x into block dimension dot x plus thread idx dot x. Basically, you're given a block id, so whatever the block dimension is, you multiply that by the block id. Why do you do that? Because it is, you'll have to account for that many threads covered for those blocks, right? So your that gives you which is 64 here and 64 into 20, right? And your block dimension is 64 rather, so it should be 20 into 64 more correctly. So your 20 into 64, and then the offset for in this particular block, the thread id has an offset of 20. So you will add that 20 to this. So 20 into 64 plus 20, which gives you 1300, as I think all of you got correctly. So let's move on to the next question. So we it's a very similar question, except we're dealing with a 2D CUDA kernel. So this 2D CUDA kernel operates on a 2D matrix M of size 2048 cross 2048 with these launch parameters. Again, everything operates on only one data point. On which data point will the thread with the thread IDX dot x0, y0, block IDX 10, block IDX y 10 operate on? And you have a few options, so try and work this out. Okay, we have one answer, which is option C. Anyone else? Anyone else? Oh, I'm happy to do that. That's the point of these sessions, right? And even if a few people get the answer and a few people don't, it's also my responsibility to try and make sure the others understand. So happy to do that, and happy it's helping you. Okay, let's look at the answer. It is 640, 640. So how do you get that, right? So it's the same logic as the previous question, except that now you need to do this along two dimensions. So we did block idx dot x into block dimension dot x plus thread idx dot x. So the same thing you will have to do along the x dimension. Then along the y dimension, you will have to do the block idx dot y cross block dimension dot y plus thread idx dot y, right? So from this launch configuration, we see that block dimension dot x is 64, block dimension dot y is also 64, and you're given that block idx dot x is 10, block idx dot y is 10, and the thread IDs are 0. So the last part of this will become 0 for both. So all you're left with is 64 into 10, 64 into 10, right? So you get 640, 640. So it's as simple as that. So if you remember that example where I think it was the 2D grid, right? This one, I think. Right, this one. So we are essentially trying to account for the number of elements in the previous blocks and then computing the offset in the current block, right? That's all we are trying to do here. So the offset in the current block is directly given to you by the thread ID, this thread ID. But what you've already accounted for in the previous blocks, you'll have to use both the ID and the dimension. So whatever is the ID, you have to kind of multiply that with the dimension, because you've already consumed, or you've already um, processed that many elements, right? So this kind of tells you the boundary of this block starting, and then this tells you the offset within that block. That is kind of the way to intuitively understand these equations. So is this clear now? Any other doubts? If not, we'll move to the next question. Consider a kernel processing a 2D matrix of dimensions 1024 cross 1024, where each thread is assigned to perform an operation on a single element of the matrix. The kernel is launched with the following configurations: A, 32, 2, 32, B, 2. For a hypothetical GPU architecture where the maximum number of threads in a block is 512, what are the values of A and B? Again, very similar question to what we did. So try solving this out. Okay, we have an answer saying A equal to 16, B equal to 8. Anyone else? We'll wait a few more seconds and look at the answer. Okay, A equal to 32, B equal to 8. No problem, that's fine. Glad you checked it and found a change. So that's okay. Any other answers? Okay, you're confused in getting the global thread ID. Let me go back to that question. Okay, right after this question, let's go back to the global thread ID and then come back to your question. Okay, before that, about the timing, I can't do anything. That's fixed kind of by NPTEL. So, and once I decide a timing, I can't change the timing for the entire course. So for this iteration of the course, it will be fixed. Maybe you can give some feedback to them saying that you would prefer sessions on certain days or something like that, and they can do something about that. But for this time, I don't think anything can be done on the timing, because they fix it at the beginning of the course. So that's fine if you're unable to join certain sessions, But whenever you're able to join, even if it's in the middle or something like that, it's still fine. Okay, let's go look at the answer. Yeah. So again, it's very similar to what we worked out previously, except that now we are told the maximum number of threads in a block is 512, right? So what is the B that would give you 512? So that you would get as B equal to 8. And then now you have a 2D matrix, so you can calculate the number of elements, which is equivalent to the number of threads, because we are told that every thread performs an operation on a single element. And then multiply this 32 cross 8 cross 2 cross 32 cross 2 into A, and equate that to this, and you will get the value of A. Because in this example, like I said in the very first question that we tried, you have two options with B equal to 8, right? So you need to go and solve for A. So that's how you get that. Hopefully this is clear. If this is clear, we can go and look at the global thread ID once and then come back to the 8th question. Let's do that. Okay, I'm assuming this one is clear since we solved plenty of questions that were similar. Right. So this slide I think has the global thread ID calculations. So let's look at it once, right? Let's take an example and maybe try going through these equations, and then that will help. So let's take this example, this particular thread. So this thread is in block 1, and its Z, Y and X are 1, 1, 3, right, going by this convention. So now let's try to compute the global thread ID, for which you need the block number and the thread number. So let's start from the beginning, right? Let's try and compute the block number. So for which you'll try to substitute the block ID x dot z, y and x into this equation. So the z and y are zeros, right? So straight away this part of it gets eliminated. You are left with just block ID dot x, which is 1. So from here we get that the block number is 1 for this particular block. Now coming to the thread number, which refers to this particular thread's number within the block. And since the threads are actually numbered here, you can see that this is 15. But let's try to work this out, right? So thread idx dot z, which is 1, thread idx dot y is also 1, and thread idx dot x is 3. And then block dimension dot x into block dimension dot y. So I think the x and y came from the previous slide, right? So x was 4, 2 and 2, right? I think so. Correct me if I'm wrong. So this was 4, 2 and 2. So now if you solve for this, you get 4 into 2, 8 plus, okay, this should be 4 again, 8 plus 4 plus 1. Or 8 plus 4 plus 3, sorry for the confusion. So that comes out to be 15, and as we can see here from the manual numbering, the thread number within that block is 15. So this tells us the thread number. Now global thread ID is actually the thread ID not just within the block but across all the blocks. So how do you get the global thread ID? So you substitute into this formula the block number across all 3 block dimensions, which I think was 4 into 2 into 2, right? That would be 16, and then the thread number which we got to be 15. So this would come out to be 31. So this means that in your first block, block 0, which you've kind of crossed to come to block 1, there were 16 threads, right? And then in block 1, this particular thread is at an offset of 15. So the global thread ID of this thread is 16 plus 15. And similarly, if I took this block and spoke about the last one here, it would be 2 cross 16 plus 15, right? 32 plus 15. And if I spoke about this one here, it would be 3 cross 16 plus 15. So you're basically trying to calculate how many threads there were in all the blocks that come before it, and then trying to add the offset of that particular thread within the block. That's what thread number gives you, offset of the thread within that block. So this is the idea of global thread ID. Now is this clear? Any doubts here? Did this help? Any other? Okay, this is clear. Good to know that. Any other doubts? Okay, so the thread number formula. How do we traverse in x, y, and z dimensions? Okay, right. I think that would be better explained if I had a figure. I don't think I have one. Let me just look through my backup slides, because otherwise I don't think it, I'll just be reading out the formula again, right? That's of no help. It's practically the same thing that's there on the slide. I think having some sort of a visualization would help you understand better. But the intuition, yeah, no worries. Thank you. You're feel free to drop off. I think we just have one question, so that's fine. Uh, yeah, the intuition again is, so this is within a block, right? So no, I think the explanation would be better with a figure. So I'll do that, and after that I think you'll understand this pretty clearly. So let's I'll again note down that question as well. Thank you for the question, and we'll get back to it in the next class. Okay, moving on. I think we have one question left. Oops. Yeah. So we finished this one. Consider a kernel processing a 1D array of 4096 elements where each thread is assigned to perform an operation on a single element of the array. The kernel is launched with the following grid and block configuration: 16, A, 2 blocks of B, 2, 4 threads. Assume a hypothetical GPU where the number of threads per block is 256. What are the possible values of A and B? Very similar question to what we discussed. Any answers to this? Okay, since we solved multiple such questions, okay, all, that's interesting. Yeah, we do have an all of the above here. Let's look at the solution. So it is all of the above. So using the same method that we discussed, first trying out that putting the constraint that number of threads in a block is 256, solving for B, and then going back and solving for A, given that you have 4096 elements, you find that all of these configurations satisfy the constraints. So this all of the above is your answer. And I think with that, we come to an end of the problems for today's session. We are well ahead of time, which is a first in all these live sessions. So I'll hang around for another couple of minutes in case there are any questions. But if not, thank you so much for joining the session, and thank you for all the interaction and the doubts and the questions. I hope the session was useful and helped you understand at least some of the concepts. And if you don't have any other questions, feel free to drop off. Thanks again for joining. Okay, thread number calculation in 3D and 2D launch is shown with the figure. Sure, I'll try to find a helpful illustration for that. And I think that was not explained pictorially in the class materials also. So it would, yeah, I agree. It would be good with a figure. I'll look for that and try to put it in before the next session. Thanks for the suggestion. I'll quickly note this down too. Anything else? Okay, I think there are no other questions, so we can wrap up 10 minutes before time. Yeah, you're welcome. Glad it helped. Thank you.